On this video, I think what I'm going to do is just work through a few examples from section 3.1, page 171 of the text. I want to work through number 27, 33, and 39, and not give a lot of commentary, not give a lot of exposition. I hope I'll talk through it as I go, but I'm just going to essentially work through this problem so that you have a reference for the work that you've done. Again, what I would recommend is you try the problem first, and then if you have difficulties, you follow along until, suppose you have a problem here, when you get to where I get to that point and you get corrected, stop the video and see if you can finish out yourself. So as long as you have difficulties, watch the video until you get that difficulty solved, but then see if you can solve the rest of the way out yourself. So here we go. I'm going to see if I can just work this out the whole way through here. So we're supposed to be finding, we're finding the absolute max and absolute min. We're going to find those values. These are going to be continuous functions on a closed interval. All right. So we got to find the derivative. The derivative here is 3x to the second minus 3x. And we're going to find the critical values. Type 1. That's where the derivative is equal to 0. And so we have 3x squared minus 3x is equal to 0. Did I copy our little problem correctly? Yes, I think I did. So here we go. So this is, I'm going to factor out 3x, leaving behind x minus 1. And so we have x is equal to 0 or x is equal to 1. So we're going from -1 to 2. So 0 is in the interval of interest. 1 is in the interval of interest. All right. So there's type 1. Type 2 critical values, that's where the derivative does not exist. All right. So since the derivative is a polynomial, that means there are none because this is a polynomial. So these are all the critical values. So round up the usual suspects. We need the original function evaluated at 0, at 1, and at -1 and 2. So we need the original function evaluated at 0. And so what's the original function? The original function is x to the third minus 3 halves x squared. Well, 0, that's easy. 0 is 0. We have x equals 1, so that's f of 1. We also, while I'm out of here, let's line them up here. This is f of -1, and we need f of 2. And so we go merrily along our little way here. 1 to the third minus 3 halves times 1 squared, which is 1 minus 3 halves. 2 halves minus 3 halves is -1/2. So far, so good. Then we have -1 to the third minus 3 halves times -1 squared, which is -1. That's +1. This is minus 3 halves. -2 halves minus 3 halves is -5 halves. And then 2 squared minus 3 over 2 times, 2 to the third times 2 squared. And so that's 8 minus, that's 4. 2 into 4 is 2. 8 minus 3 is 6. And so that's 2. So if my arithmetic is correct, let me do that real quickly again. 0, 0, 0. 1, that's 2 halves minus 3 halves is -1/2. That's right. So that's -1 minus 3 halves. So that's -2 minus 3 is -5. That looks right. And that's 8. And this is 4. 4 times 3 is 12. Over 2 is 6. That's correct. So we picked the big one. The big one is 2. And the small one is -5 halves. So we would say our final result is absolute max at, the maximum is at, remember, list the ordered pair, 2, 2, absolute minimum at, that would be -1, -5/2. And so that's my solution for number 27. All right. So, moving upward and onward, number 33. We're still going to find the absolute max and min. All right, same directions, new function here. Our new function for number 33 is y is equal to 3 minus, oh, here we go. Y is equal to 3 minus absolute t minus 3. And we're giving an interval here. The interval here is, what's my number? Where is it? Hello, eyeballs working. -1 to 5. Here we go. Yeah. All right. So see if we can work all this out here. Again, our key is now we know how to find the derivative of absolute value. Let's recall the derivative of absolute u is u over u, absolute u times u prime. So we need y prime. The derivative of a constant is 0. -1, constant multipliers multiply along, so whatever my answer is going to be negative. The numerator, I need, now anytime you have a binomial, you should write this in parentheses, over absolute. Remember, the role of u in this problem is being played by t minus 3. And then we have to multiply by the derivative of t minus 3. Well, that's just 1. And so the derivative is negative t minus 3 over absolute t minus 3. And now we continue merrily along our little way. We got to find all the critical values. This is assuming, we assume that t is not equal to 3. All right? So what do we have here? Critical values. Now, here's why this is important, because watch what happens. Here's why this piece is important. We need to assume that t is not equal to 3. We know that that's where the cusp is located, and this derivative does not exist at 3. All right? But look what happens with the critical values. The critical values here are, we treat this function just as an ordinary function here. So critical values, that's where the derivative, let's say y prime, is equal to 0. But we know how to set a fraction to 0. Setting a fraction equal to 0 means we just take the numerator and multiply both sides by -1. So that's t minus 3 is equal to 0, or t is equal to 3. So if t is 3, that is the critical value. Now, the thing is this, the function is defined at t equals 3. But the derivative is not defined at t equals 3. So this assumption applies to the derivative, not to the original problem. That's a bit of a fine point, and so make sure we have that. Assume t is not equal to 3. That assumes we're working with a derivative. The derivative, we're not allowed to have t is equal to 3. There is no slope of a tangent line at t equals 3. But there is a function value. So this, it seems odd. This actually does pass muster, because what we're going to be doing here soon is finding the original y function. So we're going to be finding y of -1. And we're going to be finding y of 5. And we're going to be finding y of any critical values. T equals 3 does work with the original function. It does not work with the derivative. Since this computation is going to be with the original function, then we do use this t equals 3. That's the logic behind this. So 3 does pass muster, even though we're assuming not equal to 3, only for the purposes of the derivative. Now this was type 1. I didn't write down. I'm not going to get full credit for my work. This is the critical values. This is type 1. There, now I get full credit. And then I have type 2. Type 2 is where the derivative, the denominator is equal to 0. T minus 3. Now, we're going to get the same solution as we had before, because absolute T minus 3 equal to 0 implies T minus 3 is equal to 0, which implies T is equal to 3. So we have the same value, but just for the record, that actually is a type 2 critical value for our purposes. And so the point is this: we have to find y of -1, we have to find y of 5, and we do have to use y of 3 because 3 is in the domain of the original function, even though it is not in the domain of the derivative. So we do need to use 3. And now it's the same thing as before. Use the original function. Y of -1 is 3 minus absolute -1 minus 3, which is, which is 3 minus absolute -4, and 3 minus 4 is -1. This is 3 minus absolute 5 minus 3, which is 3 minus absolute 2, which is 1. And then this is 3 minus absolute 3 minus 3, which is pretty clearly 0, which is 3. Pick the big one, pick the little one. So absolute max, absolute min, and we're out. Absolute max at maximum is 3, so that's 3 comma 3. Absolute minimum is at -1, so it's -1, -1. All right. Notice it's just coincidence these are repeated, because if this had been the maximum, they're not repeated. That's just a coincidence. Don't read too much into that pattern. So there's number 33 worked out. And the next thing we'll do is we'll see if we can work out number 39. I wanted to play that because it's got at least a little bit of trigonometry involved in it. So 39 will be our last of these. How are we doing our time? This video is getting a little bit, oh, not too bad. Number 39. So we have y 3 cosine of x. And we're on the interval from 0 to 2 pi. This is not required. It could be any particular interval. In fact, some of the others are different intervals. So, all right. So this is the same procedure as before. We have the derivative is constant multiplier multiplying along. The derivative of cosine is negative. I'll stick it up front. Negative sine of x. And then we got to find the critical values. Type 1. That's where the derivative is equal to 0. Divide both sides by -3 to clear that out. So this gives us that sine of x is equal to 0. I know sine of x is equal to 0, at pi, and at 2 pi. So this gives us x is equal to 0, x is equal to pi, x is equal to 2 pi. Type 2, I'll do it down here. Type 2, that's where the derivative does not exist, but there are none because this is a sine function. Remember, sine and cosine. If the domain of the function is all real numbers, you will not have type 2 critical values unless we have cusps. So since the cosine curve has neither cusps and the domain is all the real numbers, there are none of them because the function, the derivative here is sine. right? If the derivative here is sine, if the derivative has domain of all real numbers, then there will be no type 2 critical values. If the derivative has domain of all real numbers, there are no type 2 critical values. So, line up the usual suspects. We need y of the endpoint, we need y of the other endpoint, and y of 0 we already have, we don't need it twice. We don't need it twice. We do need pi. 2 pi we already have, we don't need it twice. We don't need it twice. And so what's left is to go ahead and compute this out. So this is 3 times cosine of 0. Cosine of 0 is 1. 2 pi, this is 3 times cosine of 2 pi, which is also 1. And 3 times cosine of pi, we know cosine, right? Cosine is this graph. That's 3 times negative 1, which is negative 3. Remember, if you have multiple values, list them both, or list them all. So we have the absolute max at the biggest is positive 3. So we have at 0, 3, yes, and we also have 2 pi, 3. Absolute minimum at, this is the minimum at pi, negative 3. And that is our absolute max, absolute min.